we are discussing 2D unsteady heat conduction equation, the discretization of that equation using explicit, implicit, and Crank-Nicolson method we have seen in previous lecture. In explicit method, we don't have to invert any matrix. Every equation have only one unknown, and therefore we can get the unknown by taking all the known to right hand side. In implicit and Crank-Nicolson method, we are going to have pentadiagonal matrix in two-dimensional case, and then we have to invert the matrix using methods such as Gauss-Seidel or similar iterative methods we usually employ. Our goal is to preserve the zeros, which are not possible using direct methods such as Gaussian elimination. We always hope that there will be some method where we will have this tridiagonal matrix algorithm or this Thomas algorithm we can use for multidimensional problem, and that is where this alternating direction implicit or ADI method comes in. Here we use Thomas algorithm that solves 2D problem. It can also be extrapolated to 3D, but then it's not as straightforward as in 2D. So let us see how we can do so. So consider our two-dimensional transient heat conduction problem 1 by alpha del u del t is equal to Laplacian of u in 2 dimension. In explicit method, this entire right hand side I discretize in nth time level. In implicit method, this entire right hand side is at n plus 1th time level. What we do in ADI method, I go for solving this n plus 1th u in 2 steps. I define an intermediate step n plus 1 by 2, which takes the time step of delta t by 2. And during the calculation of this intermediate u, that is u at n plus 1 by 2 level, I discretize this del 2u del x2 at n plus 1 by 2. However, the remaining part, that is del 2u del y2, I keep it at nth time level. Means this part is explicit. Therefore, if I now expand this right hand side part of this equation, the first part will look like ui minus 1j n plus half minus 2uij n plus half plus ui plus 1j n plus half divided by delta x square. And the second part is very similar, except that all of them are at nth time level. Now, if we arrange this equation properly, you see that I have kept this n plus 1 by 2 on left side and remaining term on right hand side. All the terms on right hand side, you see that they are at nth time level and therefore they are known. However, the terms on the left hand side, they are unknown. But see that every equation contains only 3 unknowns. And thus, if we write them in a matrix form, it will be a tridiagonal matrix, because you see with ij, I am getting I minus 1j, I plus 1j. So this will become a tridiagonal matrix. So then, if I solve this tridiagonal matrix, what I will get is u n plus 1 by 2 for all ij's. Now I will take this. My solution is incomplete because what I want is that uij at n plus 1th time level. So what I will do now, I will go to step 2. And in step 2, I will solve un plus 1 ij minus uij n plus half divided by delta 2 t by 2, because I am going from this half step to full step n plus half to n plus 1. So once again I am going half time step Here I have kept the x just the same at n plus 1 by 2 time level, but now I have calculated this u value of n plus 1 by 2 from step 1. So now when I am at n plus 1 by 2, this part is known. That is del 2x del x to n plus half. This is known. The only unknown is del 2t del y to n plus 1. Previously it was at n, now it is at n plus 1. If I expand this right hand side, it will look like ui minus 1j minus 2 uij plus ui plus 1j at n plus half divided by delta x square, and here ij minus 1, ij and ij plus 1 at n plus 1 time level divided by delta y square. So if I bring this n plus 1 to left hand side and remaining part I keep at right hand side, you can see that at right hand side all the terms that I have, they are at n plus half time level, which means they are all known. I have solved them in step 1. Now you look at the left hand side. Here I have 3 unknown per equation, and therefore we should be able to solve it using tridiagonal solver. So what I did, when I was going for an implicit or Crank-Nicholson method, I was inverting a pentadiagonal matrix. Here I am performing equivalent to that, inverting tridiagonal matrix twice. The good thing about working with tridiagonal matrix is that we have a direct solver available for that, very efficient solver, Thomas algorithm. So we are not going for iterative method. Instead, we are going for direct method. That is the advantage of this. One of the problem of using Thomas algorithm or this TDMA, tridiagonal solver, is that as we go from bigger and bigger matrix, so when you are solving an n by n matrix using TDMA, as n grows, this matrix can become slightly unstable. So you have to be careful about the quality of solution at that time. But other than that, this is actually a very good method and very popular method indeed, especially for 2 dimension. As we go and apply this method in 3 dimension, then it's not so easy. The implementation is way more complicated than 2D. There are several options, of course, for 3-dimensional implementation of this, but let us not go into that detail. In 2 dimension, this ADI method is a very popular and very efficient method in general for unsteady diffusion equation. So now we have seen the ADI for 2D problem, and for your exercise, you take this usual diffusion equation in 2 dimension. Now you want to solve in a square domain using ADI. You write a pseudocode for this. Carefully write how you will treat the boundary conditions. This is very important in ADI. You have to properly implement the boundary conditions. Otherwise, you will get wrong results. So that's all for this lecture. Thank you, and I'll see you in next class.